Hi everybody. This video is going to be pretty much an overview of everything we learned this year and some important things that you should memorize going into our Regents exam this week. So let's start off in Unit 1, which was all about polynomials. The first thing we learned how to do was to long divide. You could also reverse tabular, but you should know how to do a long division problem or a reverse, or to use the reverse tabular method, because those are easy points to get. Reverse tabular. Long division and reverse tabular is a great problem because it's going to pop up in multiple ways, because we can use long division to see if something is a factor. If the remainder is 0, then the divisor is a factor. So if I divide by some divisor and get a remainder of 0, then that divisor is a factor, and that's definitely going to be on the test somewhere, somehow. That is this a factor? Well, it's only a factor if you have a remainder of 0. And a way that we can check this, if I had some polynomial divided by x minus a, the remainder theorem tells us the remainder. Well, how do I just check the remainder if I want to do some polynomial divided by x minus a? Is plug in a positive a. Plug in that opposite number there, plug in the associated 0 with the divisor, and that'll tell me what the remainder is when I divide p of x by a. So the remainder is p of a. So that's a very, very quick way to use the remainder theorem here to do a long division problem and to check your remainder, or to see if something is a factor by seeing, do I get a remainder of 0? Speaking of factors, we need to know all of our factoring techniques. Well, the first thing we always need to look for when we factor is a GCF. A GCF is our starting point. From there, if I can take out a GCF, I'm just making my life easier. Over here, I have two terms. I have a binomial if I'm trying to factor something with two terms. It's one of two options. It's the difference of perfect squares. It's the difference of perfect squares, just like 9th grade went. X squared minus 49 becomes x times x is x squared plus 7 minus 7. We should have that pattern down cold. Notice, we only factor the sum of perfect squares and throw an I in there if we're solving equations. Be careful factoring the sum of squares. We only really do that when we're solving, and we throw an I in there at the end. If not, don't touch your sum of perfect squares, just leave them alone. It could be perfect cubes as well. And this is more of an Algebra 2 factoring technique because we didn't do this in 9th grade. So just an example here. If I have smiley face cubed minus star cubed, we'll go with. If I have something cubed minus something else cubed, this could have also been a plus. You have a linear factor, and you have a quadratic factor. The linear factor is kind of the starting point. What gave me smiley face cubed? Well, smiley face. What gave me star cube star? And because there's a minus sign there, I'm going to put a minus sign there. That linear factor is the important part because it's going to help us get this quadratic factor over here. Well, it's a pattern that you kind of need to memorize. Square the first, multiply them, square the last. And the signs go the same sign as whatever I started with, the opposite sign, always positive. We love our acronym SOAP, but it's same, opposite, always positive for when we factor perfect cubes. So if I asked you to factor x cubed plus 125, you need, okay, I need a linear factor. That's x and 5, because x times x times x is x cubed. 5 times 5 times 5 is 125. And I have a plus sign. My quadratic factor will follow the pattern. Square the first, multiply them, square the last. Same, opposite, always positive. Those are how we deal with perfect cubes, and that's when I'm factoring something that has two terms but is not the difference of squares. Okay. Just move that over here to give myself some room. Three terms Well, if something has three terms, it's called a trinomial. If I have a trinomial, it's one of two cases. It's either a nice ninth grade problem, x squared minus 6x plus 8, where you say self, when we factor trinomials, we ask ourselves two questions. We say self, what multiplies to 8 that adds to negative 6? Well, what multiplies to 8? I'm thinking of 4 and 2, but they're both negative. Yes, that checks out. And those would be the factors. However, if I was factoring something with a leading coefficient other than 1, and remember, I already took a GCF out, so I cannot take a GCF out of 3x squared minus 10x minus 8. If I want to factor this trinomial, I've got a leading coefficient there, so I need to use the AC method. I need to ask myself, not what multiplies to negative 8, what multiplies to 3 times negative 8, which is negative 24. That adds to negative 10. And when I get these two numbers here, I'm going to use it to split up that middle man. I'm going to take that linear term there and split it into 2. So what multiplies to negative 24? They need opposite signs, so negative 12 and positive 2. So using that, I can split up that linear term there, that middle term, and make it 3x squared minus 12x plus 2x minus 8. I took that negative 10x and just simply rewrote it. Then we group, which we're going to talk about in a minute. I've got 4 terms now, so I can take out a GCF from the first 2 terms. I'd better have that same factor over here. Now, what's my new GCF? I now have 2 terms. My new GCF is a factor of x minus 4, and I'm left with 3x plus 2. That's how I factor that polynomial right there. So the AC method, when I factor something with a leading coefficient bigger than 1, I ask myself, what multiplies to a times c, the first and last numbers that add to the middle term? Once I get those two numbers, I don't jump to parentheses like I did in that easy first problem there. I have to split up the middleman and group. Which brings me to my last technique of factoring. If I have 4 or more, if I have a polynomial that has 4 or more terms, that's going to be some form of grouping. I think you guys are really strong with grouping, so I'm not going to spend too much time talking about it, but we did grouping right here. If there's 6 terms, remember, do not try to combine like terms there. Do not try to combine the like terms. Just use the structure they gave you to group. If all else fails, combine like terms, but please don't. Use your calculator to help you factoring too. A lot of the times, you can answer a multiple choice question by throwing one side into y1 and the other side into y2 and seeing that both of them are equivalent. They create the same table for all values of x. So factoring, we have 2 terms, trinomials, and grouping. Why do we care about factoring? Because factoring helps us graph our polynomials. That's how we ended this unit, was by graphing our polynomials. When we graph, there's a couple things we've got to look out for. Our zeros. Our zeros are real zeros. I'll emphasize that. Our real zeros are where we hit the x-axis, where we cross the x-axis. So I'm not going to say cross. I'm going to say intersect the x-axis. So, for example, this polynomial here, I know there's 3 real zeros. There they are right there. I've circled them because that's where it crosses the x-axis. So the zeros are an important feature, and the end behavior is also an important feature. The end behavior depends on 2 things. Is my degree even or odd? Is my highest power even or odd? And I know right now you're doing the dance, even, odd, odd. Am I even or odd? Is my degree an even degree? Do I have an x to the 4th, x to the 6th, x squared, or do I have x to the 3rd, x to the 5th, an odd degree? And then we look at the leading coefficient. The number that goes with that highest power term, is it positive or is it negative? Those are what matter about end behavior. So in this case here, doing my dance moves, even odd, I know I'm an odd degree positive. This is an odd degree with a positive leading coefficient based on, as x approaches infinity, where is my function going? Here it's skyrocketing up. My y values are going where? As x approaches negative infinity, where are my y values going? So that's what our end behavior is describing with polynomials. So a couple key features with polynomials are our real zeros and our end behavior. Another quick note about zeros. If I have a repeated root, if I have a repeated zero, a multiplicity of 2, I have 2 of them, it's going to touch the x-axis and turn around. So I know at this point right here, that 0 right there is a double 0. Why? Because it kissed the x-axis and then turned around. Whereas over here, I know I only have one of them because it crossed through. It crossed through, so I just have one of those zeros. But when I kiss the x-axis and turn around, that is a double 0. So this was Unit 1. Unit 1 was packed full of information, which is why it was the unit that never ended. But some big ideas that come from Unit 1, division and the remainder theorem, all of our factoring strategies, and putting those together to sketch graphs and to graph polynomial functions. So continuing on to Unit 2, Unit 2 is more of an algebra chapter than understanding concepts chapter. So the first thing we did in Unit 2 was we solved rational equations. We solved rational equations. And when I say rational equations, I'm talking about equations with fractions. There was a couple steps here. When we solve an equation with a fraction, our game plan is to get a common denominator. Once I get a common denominator, all we're going to look at is we're going to look at the numerators. We're going to equate the numerators. Once you do that, you're probably going to get a quadratic, maybe a linear equation, and you're going to solve that equation, solve for possible solutions. Remember, these might not actually be the actual ending up being solutions to our original equation. We're just solving for possible solutions. The last step when we deal with rational equations is we need to check for undefined. We need to check for extraneous solutions. We need to check for extraneous solutions. And the key thing here is it's going to be dividing by 0. If I plug the number back in, do I end up dividing by 0? Because remember, that's the one numerical operation we can't do is divide by 0, which we say is undefined. It makes it undefined. So that's how we solve a rational equation. We get a common denominator. Once you get a common denominator, you multiply the bottom and the top by the same factor. You equate the numerators and solve that resulting equation. If it's quadratic, you're going to set it equal to 0 and hopefully factor it from there. Once you get your solutions, you then have to go back and check. You have to check the denominators and make sure you're not dividing by 0. You're not making an undefined value. Solving square roots, solving radical equations, ones with square roots in it, our first step is to isolate. We want to isolate the square root. You want to get it all by itself. You want to isolate the square root and then square both sides. Why do I square both sides? To undo the square rooting. But I'm not going to square anything until I isolate the square root. Once I isolate the square root and square both sides, we solve for possible solutions. These are our candidates that might be solutions, but squaring is kind of an illegal thing. Just as getting a common denominator, it's illegal because we're possibly adding in extra answers. Then we check by plugging back in. Let's stay with blue here. We check by plugging in. And if it doesn't work, it's an extraneous solution. If it works, it's a solution. With multiple choice for both rational and radical equations, please use your calculator. Take your answers and plug them back in. Use your calculator to assist you because it's going to get you free points on multiple choice that a free response question might not. Solving a 3x3 linear system. Solving a 3x3 linear system. This is when we use elimination. I'm not going to get into it in this video of how we do that process, but make sure you check out the Unit 2, the end of Unit 2. I want to say it's Unit 2, 7 to 9 possibly, videos. That'll walk you through how to solve a 3x3 linear system with elimination. We've done practice problems, and if you remember how to use your calculator and a matrix to get the answers, that's an excellent skill to have coming in, so that way you at least know what your answers are. Well, it's not part of Unit 2. We kind of did it in the beginning of Unit 3. I'm going to write it now. Solving a quadratic linear system. So this is when I had a parabola and a line. I could have two solutions. I could have one solution, as shown here, or I could have no real solutions, where the parabola and line never touch. Same thing goes with circles. I could have had a circle and a line. I could have had a circle and a line that's tangent to it, or I could have had a circle and there's no intersections. So when we solve a quadratic linear system, we're looking for coordinates x and y. We're looking for actual points. So once you get x, you're not actually done. You then have to substitute back in to get your y values because you're looking for the coordinates of the points of intersection. And the way that we do that is with substitution. We use substitution. Once I get y equals, I'm going to pick that up and plug it on in into the other equation for y and then solve that equation. So we use substitution to solve a quadratic linear system where I have a parabola and a line or a circle and a line. Probably you're going to end up with a quadratic equation that you have to solve. Hopefully it's factorable. If not, you can use the quadratic formula to solve it to get the solutions. So Unit 2 was packed full of solving. It was a packed full of solving where we had rationals, radicals, and systems. Unit 3 was all about quadratics in terms of complex numbers. Unit 3 is where we made up our new number. We had our complex number system. We had the complex numbers. You guys are pretty strong with this, but make sure when you reset your calculator, you go to your mode and go to A plus BI mode so that you can use your second decimal point, which gives you the imaginary unit I. When we work with I, you really just have to know I squared is -1, because from there we get everything else. Every two i's become a factor of -1. And if you need I to the 5th, I to the 18th, you can use this relationship here that I squared equals -1 to figure out the value of that. Be careful when you square something, make a table. When you square it, make a box and figure out the terms, all four terms in that box. I'm not going to do any problems with complex numbers because we did a lot in class, but I squared is -1 is the essential relationship that you know for when we work with complex numbers. Well, why did we come up with complex numbers? Because when we were using the quadratic formula, we were ending up with things like the square root of -16. And in Algebra 1, we quit and said there were no real solutions. But now we're going to say, wait a minute, let's take out an I, because I is the square root of -1, and call this new complex, this imaginary number here, 4i. So if I had the square root of -45, the first thing I'm going to do is take out an I, and then tear apart 45, because that's not a perfect square, into 9 and 5. We need to remember how to simplify radicals. 3 square roots of 5i. So we do this process when we're solving quadratics with complex number solutions. So when we solve quadratic equations and you see something that looks like 4 plus or minus the square root of, I don't know, 7 over 2i, you need to recognize if you see multiple choice answers like that, or if in the free response you're asked to just solve this quadratic equation, chances are you're going to be using the quadratic formula. And I know you're singing in your head right now, x equals -b plus or minus the square root of b squared minus 4ac all over 2a. When we use the quadratic formula, we pick the coefficients off of ax squared plus bx plus c equals 0. You have to make sure your quadratic equation is set equal to 0, and then you can pick those three coefficients off and plug them in. Be careful with the b squared term because you're going to square a negative number probably. Make sure that b squared term comes out positive. Once you plug numbers into the quadratic formula, plug in the b squared minus 4ac, don't type in the radical, and go from there. But that's why we came up with our complex numbers, is because we wanted to solve every quadratic equation, and we needed this new number I to help us out. The end of Unit 3, actually in the beginning of it, we talked about the definition of a parabola, where we defined a parabola as the set of points equidistant from a focus, which is a point, and a directrix, which is a line. I have a whole separate video on the Google Classroom for you to watch it with problems relating to focus and directrix, but you need to remember that idea that, okay, if I have a directrix and a focus here, the first point that I need to find is the vertex, which is equidistant between the focus and the directrix. The parabola is the set of points equidistant from the focus and directrix. Any point from the parabola to the line, parabola to the focus, those two distances will always be equal for every point on the parabola. And we use our formula, vertex form of y equals 1 over 4p times x minus h squared plus k to deal with these focus directrix problems. I'm not going to say any more about it, but go watch that other video on the Google Classroom because it's been a while since we've done any focus directrix type of problems. Unit 4 is where we hashtag get triggy with it. Unit 4 is all about our trig functions. There's two parts to this unit. The first half is dealing with the unit circle and extending our idea of the trig functions from sides of triangles to kind of an angle rotation. When I spin on the unit circle, I spin counterclockwise, and the terminal side is the hypotenuse of the triangle that I'll be making. So we start at the positive x and spin counterclockwise. We always drop perpendicularly back down to the x-axis to make a right triangle. When you see a right triangle, you should be able to label the sides regardless of what quadrant it's in. I like to just draw this picture in quadrant 1. But regardless of what quadrant I'm in the unit circle, so I have a radius of 1, the vertical distance is sine because that's the opposite side of my reference angle. The vertical side of the triangle is sine, whereas the horizontal distance, the x distance, is cosine. So knowing this picture here is beyond essential for dealing with all problems related to a unit circle, because our y values, our vertical distance is our sine of theta, and our horizontal distance, our x values, are the cosine of theta. From this one picture, you get the idea that x is cosine and y is sine on the unit circle. You also get the Pythagorean identity. To prove the Pythagorean identity, once we know that x is cosine and y is sine, using the Pythagorean theorem, we get leg squared plus leg squared equals the hypotenuse squared. Well, 1 squared is just 1. So we get the Pythagorean identity here, sine squared plus cosine squared equals 1. And we also get what tangent is. We also know from this unit circle that we can define the tangent of theta, soca toa, opposite over adjacent, as the sine of theta over the cosine of theta. So from the unit circle, we get all of these pieces right from this one picture. You get that the x, the horizontal, is cosine, and the vertical is sine. You also know when things are positive and negative. In quadrant 1, both of them are positive. As I spin into quadrant 2, only my sine values are positive. Only my tangents are positive in quadrant 3, and only my cosine values are positive in quadrant 4. That goes back to the idea that cosine is x and sine is y. So you need to know that all are positive in quadrant 1, sine is positive in quadrant 2, tan is 3, and cosine is 4. One more thing about trig in the unit circle is we have our 3 trig functions to start with, but then we have the 3 reciprocals. We have our cosecant, our secant, and our cotangent functions. You need to know that who these reciprocals come from. And it's important that you don't call them opposites. Please call them reciprocals, because that helps you remember that cosecant is 1 over the sine of theta, secant is 1 over the cosine of theta, and cotangent is 1 over tan theta. It's the reciprocal of tangent, so it could be cosine over sine, because tangent started out as sine over cosine, so cotangent is the reciprocal of that, cosine over sine. You need to know your reciprocal identities, because those can come up. We need to know that cosecant is sine. Please, please, please make sure that you don't say cosecant's cosine. It's not nice where the c's line up like that. Cosecant's the reciprocal of sine. So this is all related to our unit circle. The key thing is to draw a picture if you can. Chances are you're drawing a picture and using the Pythagorean identity or theorem to find the missing sides. So those are basically your steps when we deal with finding trig ratios in any quadrant. Draw a picture. If it's the unit circle, great. If not, you're going to have to use the Pythagorean theorem to find the missing side. The second half of trigonometry dealt with graphing, unwinding our trig functions from the unit circle and graphing them over a rotation. One more comment before I move on from that. You need to know what a radian is. A radian is when you take the radius and spin that much, and pi radians get you halfway around the circle. Pi radians is 180 degrees. That's a lovely key fact that you should keep in your back pocket. It's also on the reference sheet, kind of, that pi radians is 180 degrees. Pi radians is a half a turn around the circle. 180 degrees gets you to pi radians. 1 radian gets you 1 radius. I go out the radius, I spin that much, that distance is the same. But pi of them, 3.14159, radii of a circle will get you halfway around regardless of how big that circle is. Back to graphing. You need to know what your parent sine and cosine functions look like. Your parent sine curve is little hill, little valley, and there's 5 key points. It starts at the midline, max, midline, min, midline. From the unit circle, since these are my parent functions, I go -1 to 1, and it has a period of 2 pi. The period is how long does it take me to complete one curve, one full cycle of the sine or cosine function. Cosine is one big valley. Cosine is one big valley. It starts up at a maximum, midline min, midline maximum, and it has a period of 2 pi as well, because it takes me 2 pi radians to spin around the unit circle. If I stick a negative out front, that's reflecting it over the midline, so you'd get a little valley, little hill, or a big hill for negative cosine. Sine always starts at the midline. Cosine always starts at a maximum or a minimum. Those are just some ideas to keep in mind. We then looked at trig functions by saying, let's transform them by sticking a number out front. Same thing goes for cosine. Sticking a number in front of x and adding a number on at the end. That number at the end is our midline of y equals k. Y equals k is the midline. It's not just k, it's y equals k. Is the midline. That's what we oscillate around. That's like our home base. The midline is where we always start when we deal with our trig graphs. From there, we go up and down the amplitude. From there, we go up and down the amplitude. So I go up a units and down a units. It's the vertical distance from this midline up to the maximum or minimum. So here I know I have a midline of k. I have to add on a and subtract away a to get my maximum and my minimum. This number in the middle here is kind of useless, but it helps us get the period, because b, that number, times the period always equals 2 pi. The coefficient of x times the period, this number here either speeds up or slows down how fast this trig function oscillates, will always give us the period. So the frequency times the period always gives us 2 pi. When you graph, you always have to label where did that first cycle end, otherwise I'm not sure what your x-axis is scaled by. So when we graph trig functions, a is the amplitude, b is the frequency, which isn't helpful, but the period is, that tells me how long one cycle is, and that number at the end is the midline. Unit 5. Unit 5 was all about exponential functions. And it's very closely related to Unit 6, so these might get merged into one kind of idea here. But exponential functions, we started with our properties of exponents. We started with our properties of exponents, and we defined, how do I define x to the a over n? Well, we know that over n, that dividing by n in the exponent is taking an nth root. I'm taking an nth root of x to the a. So this is power over root, where I have the numerator stays as the exponent, stays as the power. The denominator is telling you what type of root, what type of radical, the index of your radical that it becomes. So if I have x to the 4/7, I know I have that over 7, so I'm taking the 7th root of x to the 4th. That fourth power can go inside the radical or it could go on the outside. Either place is appropriate. As we talked about in class, New York State loves to have you explain why this is true. We'll just talk about, well, I have that 7th root, that over 7, so I'm going to be using a 7th root. Just don't do math. Make sure you're using words. All properties of exponents are in play. So if I'm multiplying two quantities, I add their exponents. If I'm dividing two quantities, I end up keeping the base and subtracting the exponents. And if I have a power to a power, I keep the base and multiply the exponents. All three of these rules are in play when we're working with these fractional exponents, and we've done plenty of problems where you've had to use all these properties of exponents in them. So the key thing here is this fractional exponent will be somewhere on your test. It's the power over the root. It's my exponent stays as an exponent, but that divided by becomes your root. We looked at graphs of exponential functions quickly, where there's two cases. It's either exponential growth or it's exponential decay. Is it increasing or is it decreasing? And it doesn't matter what it is, both of these exponential functions have a horizontal asymptote where it gets really, 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 really close to it, but it never touches it. So it has a horizontal asymptote. Normally it's the x-axis, it's y equals 0, but that can change depending on how you transform them. Many times you're asked to graph ugly exponential functions. Just use your calculator in your table to help you out graphing these exponential functions here. The key thing that we did with exponential functions is we wrote models. We wrote exponential equations that modeled given scenarios, and they were generally in the form of a principal amount times some multiplier, and then t, and we might have to do something to that exponent. Normally, so if we're doing a half-life problem, it would be t over the half-life. How long did it take? So in this case, it would be a 1/2 multiplier, and my initial amount would be out front. But the key thing is when we work with exponential models, your variable is in the exponent. So working with half-lives, it's okay, it's my initial values out front, whatever I'm multiplying by. It could be a half-life, it could be a triple, it could be a grow by 15%. Well, how do I grow by 15%? I add a 1.15. It could be decay by 7%. Well, that's 1 minus 0.07. Remember, divide that by 100 to get 0.93. So you always have to be careful of what your base is in your exponential function. There's two formulas you need to memorize when I'm compounding money. When I'm compounding interest, there's two formulas. There's the annually, monthly, semi-annually, quarterly. That's P times 1 plus R over N to the NT. That deals with how often, the N deals with how often I'm compounding the money. So if I'm doing it 4 times a year, I'm going to take my annual rate and divide it by 4 because I need to get to a quarterly rate. If I need a monthly rate, I'll take my rate and divide it by 12. If N approaches infinity, if you keep compounding it so that it's happening continuously, This p times 1 plus r over n to the nt, something that you need to memorize, will become everyone's favorite PERT, where e is that lovely irrational number, that transcendental number 2.7182818284595. You need to know where that e button is on your calculator. There's 2 spots for it. Take a second to find them. So if we keep compounding every instant, every second, this formula transforms into PERT. Those are 2 formulas that you need to memorize, as well as having this overall idea of how do I deal with half-lives? How do I deal with bunnies tripling or doubling? How do I deal with the ant population growing by 15%? It's your principal amount times whatever your multiplier is to the t over how long. So if the half-life is 8 days, I'm going to do t over 8, because I don't want it to happen every day. I want it to happen every 8 days. With these exponential equations, there's either 2 types of problems it could be. You can plug it in, or you might have a variable stuck in the exponent, which brings us into Unit 6, which deals with logarithmic functions. So the reason why we came up with logarithms is because it helps us solve problems when our variable's trapped in the exponent. So example, we've done a half-life problem where we ended up with 7 equals 20 times 1/2 to the t over 8.02. But my variable, it's so high up there. When my variable is trapped in the exponent, we're going to end up using a logarithm to bring it back down. But the first I have to divide by 20 to get rid of that 20 there. So I get 0.35 equals 1/2 to the t over 8.025. Now that I got this exponential expression all by itself, I can apply a logarithm. I always use natural logs, but you can use a plain old log log, and by doing so, it lets you drag the exponent down front as a coefficient. And I have the ln of 1/2. So by using a natural logarithm or a logarithm, it allows us to take our exponent and drag it down front. And here you would just finish solving by multiplying by 8.02, and then dividing by the ln of 1/2. Please use the fraction button when you deal with these problems, because those can get very nasty. But we use logs to solve exponential equations when the variable's trapped in the exponent. We use logarithms because my variable, it's so high up there. How can I bring it down? You use a logarithm. We graph logarithmic functions. It's the inverse of an exponential. So it looks like an exponential function, but it's been reflected to look like this. So it has a vertical asymptote, normally at x equals 0, but that can get translated around. Make sure you follow the directions. There was a problem that asked you to graph both the y and x intercept. Make sure you show all those graphical features. But this is a logarithmic function here. On your calculator, make sure you use the log base button, which is hidden in math, to graph other logs than ln or log. The log log is a base 10. The natural log is a base e. So you make sure you know the difference between those 2 logarithms. What else is there about logarithms? That's pretty much all we did with them. That's pretty much all we did with logarithms. Just remember that logs are exponents. Log is the what power function. Logs equal an exponent. So they're very closely related to exponents because they're the inverse. So we should probably talk about inverse functions. If I have an inverse function, it means I'm taking my graph and reflecting it over y equals x. So our game plan, algebraically to find the inverse, is to switch x and y and solve. We switch our independent and dependent variables. We switch x and y and solve. And the notation we use is that f to the -1, the f inverse of x. We've practiced some of these problems before. I'm not going to say much more about inverses, but make sure you can do an inverse problem, because this is a problem that can be very doable. It's this f inverse notation here that you just need to look out for. So we switch x and y and solve for our y to find our f inverse, to find our inverse function. That's really it with logs. We use logarithms to solve exponential equations is the key idea. We use these logarithms to solve exponential equations. Unit 7 is still kind of related to the previous 2 units. It's when we dealt with sequences and series. Sequences, there's two types of sequences. You can have an arithmetic sequence. Well, I mean, you don't have to be arithmetic or geometric, but these are the two sequences that we care about. There is a neither category. There's a whole bunch of neither, but we don't really focus on them. An arithmetic sequence, we're adding a common difference. We're adding that same number each time. That's called the common difference. Whereas a geometric sequence, we're multiplying by a common ratio. You want to figure out what number I keep multiplying by to get to the next term. Arithmetic sequences are written explicitly. This is on the reference table. A sub 1 equals d times n minus 1. This is on the reference sheet, so you don't need to memorize that. But that's the formula for the nth term. Should probably write the right formula. A sub n equals a sub 1 plus d times n minus 1. And geometric sequences are a sub n equals a sub 1 times the common ratio to the n minus 1. So they have the same form. The common difference is just adding. The common ratio is just multiplying. Those are on the reference sheet. Those are explicit formulas. If you want the millionth term, you plug in a million. If you want the 200th term, you let n be 200. So whatever term number you want, you plug it in. Versus writing them recursively, it describes the pattern. And there's two parts to a recursive formula. You have to tell me where to start, and then you tell me, how do I get to a sub n plus 1? How do I get to the next term? Well, I take the one before it and maybe add, and I won't do add 7, maybe you add 5. Because here's a sub n. Who's next in line? The a sub n plus 1th term. Who's before a sub n? A sub n minus 1. So a recursive formula is describing the relationship between those two terms in a sequence. So sequences in series, we mostly use them to model. It'll probably be in some kind of modeling situation, but it's closely related to linear and exponential functions. There will be some kind of series problem, and it will most likely be a geometric series. A series means I add up all the terms. It's the sum of the terms. It's the sum of the terms of a geometric sequence. And there's a formula given to you that adds up all the terms that we derived in class of a geometric series, where all you need is the first term, the common ratio, and how many terms. Normally these are hidden in terms of Brian putting 1 cent, then 3 cents, then 9 cents, and then 27 cents in the bank, or the ball falling and I want to find the total distance. The key thing is we're finding a total. We're not just finding the 20th term, we're taking the 20th term and adding it to the 19th, 18th, 17th, and we're adding up all those terms. The key thing with the geometric series is we're finding a total. Be sure to look over some geometric series problems because it could pop up. Series, sometimes we use sigma notation, we use summation notation to represent the series where this is the first number you plug in, and then you plug in a 2, then you plug in a 3, then you plug in a 4 until you get to the highest number, let's say a 6. The highest number you plug in is 6, and then you stop and you add them all up. So sigma notation, there'll be some kind of function here where you plug it in, get an answer. Plug in 2, plug in 3, and then you're going to add those all up. But geometric series are the key focus of this class. There can be the mortgage problems. Make sure you look out for important things like down payments. And check over those videos and those problems. We've done a couple of them. We did the Buying the House project. Make sure you are comfortable plugging into those formulas, and make sure you plug in them correctly. But that falls kind of under this geometric series because that's where they come from. Unit 8, we're almost done with Algebra 2. Unit 8 was all about probability. Probability, there's very few ideas you need to know, but you need to know these ideas well. You need to know what P of A given B means, and you need to have an understanding more than just a computational fluency with it. P of A given B means B already happened. I know B happened. I'm not going out of the total, I'm just going out of B. B becomes my new universe. And since B already happened, I want to know what's the probability of A, but B already happened, so it's and over given. It's the and probability over the given piece. It's A and B over B. It's not just A because I know B happened, so I was given B happened. I want to know what's the probability A is happening now. Conditional probabilities are a big idea because it helps us talk about independence. Did one event affect the probability of the other event occurring? So the way that we do it is we find a probability. You find the probability of male. You find the probability of A happening. Then you still find the probability of A. You still find the probability of male given something else happened. Notice that A is still in the front seat. You found the probability of A, you're still finding the probability of A. This time you're just assuming that B already happened. You want to know, are they equal? If they're equal, knowing B happened didn't change the probability of A, so they're independent events. But if they're not equal, they are not independent. That's mostly what I use with two-way tables. If I'm given word problems, my chances are I'm going to use this test. I'm going to multiply A and B and hope, do I get A and B? Do I get the middle intersection? So when I work with two-way tables, I use this conditional probability. When I work with word problems, chances are I'm going to multiply the two probabilities and see if I get the intersection, and see if I get the and. Make sure you can do independence because it's a huge idea and it's going to show up somewhere, somehow. The last idea we need to really deal with is the OR formula. P of A or B, that union of A or B. Well, we add A and B together. You add A and B together, and the minute you see OR, you got to be thinking about this formula, and then you're going to subtract away the middle piece. You're going to subtract away the and. Because if I was to look at a Venn diagram, I counted the middle twice. If I add up A and B here, in doing so, I've counted the and probability twice, and that's an issue. So that's why I subtracted away once. So we need to know our conditional probabilities, we need to know independence, and you need to know how to work with the OR formula. You need to know how to work with the OR formula. That's all there is to probability, which is a fantastic thing because it's hard enough as it is. Let's just keep it to these three ideas. Unit 9 is statistics. We have our inferential statistics unit, the last unit that we just talked about. You have to know how to work with normal curves. You need to know how to work with the normal distribution, which is using normal CDF, which is second vars, which brings you to your distribution tab, and it's choice 2, normal CDF, where you type in the lower z-score and then the upper z-score into the normal CDF. Well, what's a z-score? A z-score is how many standard deviations away from the mean are you? How many standard deviations away? So you do the value minus the mean and divide that by in terms of how many standard deviations am I away. That's how you compute a z-score. And when we find the probabilities, draw a picture. The mean goes in the center. And here's my z-score. You might want to know what's the probability I'm less than that z-score. So I type in negative infinity or negative 1,111,1,1,0,0,999, whatever numbers you want to use to the upper bound of z. Or maybe you want to know an in-between probability so you know your lower and your upper z-scores. But just use your calculator and use normal CDF to deal with normal distribution problems. Then we talked about surveys, observational studies, and experiments. I'm not going to write much down, but I am going to talk about surveys is when you ask people questions. You ask a question, and hopefully you have a random sample. You want a sample that reduces the bias by randomly asking people. So maybe you ask the 10th person entering the school, or maybe you ask I don't know, every 5 people entering the lunchroom. You have to make sure that you have a random sample that's free of bias and actually represents, the sample should actually represent the population you're talking about. An experiment, you're applying treatments. You're applying treatments randomly by random assignment. You randomly assign people to the treatments, and you should have some control group to compare it back to. You should have some control group to compare your results. And once you have random assignment, you can establish cause and effect between your variables. Once you have that random assignment, it lets you establish that there was actually cause and effect between the variables. So you need to know the difference between survey, observational studies, and experiments. Because from a survey or an experiment, we're going to make inferences. We're going to make inferences with a sampling distribution. By using some kind of simulation, we're going to be creating a sampling distribution for our p-hats, our sample proportions, or our x-bars, our sample means, to make guesses to estimate the parameters. Our whole purpose of inferential statistics is, okay, I have a sample statistic. What's my best guess for this population parameter? And the way that we normally do that is from our sample statistic, we're going to develop a confidence interval. We're going to develop a 95% confidence interval by going from the mean up or down 2 standard deviations of the sampling distribution. To be 95% confident, we're going to take our mean, our sample mean, and go from the sampling distribution and go up or down 2 standard deviations. That 2 standard deviations piece, that little wiggle room you're giving yourself, is the margin of error. That 2 standard deviations you give yourself is the margin of error. That's just a term that you add and subtract from the center of your sampling distribution to create the confidence interval. And when we're doing 95%, it's 2 standard deviations. When we work with our difference of sample means, find the difference, and I want to know, is it significant? Is it statistically significant? Well, when we do that, from my dot plot, once I find my difference of sample means, once you find your difference, you're going to go to your dot plot and say, okay, here's my x bar diff, and count up, and is that less than 5%? If it's less than 5% of the time, it's an unusual value. It is statistically significant. It is significant because it's so extreme, it didn't happen by chance. Because I'm all the way out here, we have evidence that it happens less than 5% of the time, that it is an unusual and statistically significant because it's that far away. That's mostly when we deal with our difference of sample means, is we go to our distribution, draw it in, and count up, or if I was down here, I would count down. I forgot to mention, when we work with confidence intervals, first of all, round correctly, and then answer the question. Is it in the interval? That's normally a follow-up question. Is it in the interval? Is it in the interval? Or is it not? If it's in the interval, it's a possible value. If it's not in the interval, it's probably not a possible true population parameter. So be careful when you're working with confidence intervals. Is the value in the interval, or is it not in the interval? But when we work with our difference of sample means, we're going to say, okay, here's my difference, here's my sampling distribution. Is it extreme enough? Is it happen less than 5% of the time that I can say it is statistically significant? Before I end this lovely review of everything, there's a couple tie-ups that I want to do. Transformations, regardless of what function I'm working with. If I have a number inside, it's shifting it left or right, and it's opposite. And if I have a number on the outside, that's up, down, and it goes the right way. So that inside transformation moves you left or right and is opposite. Up or down is on the outside and it goes the way you want it to go. Intersections. That's when we solve, when does f of x equal g of x? When do these two crazy functions equal each other? That's Mr. Blinks. Mr. Blinky will tell you where they intersect. When you solve f of x equals g of x, it's just an x equals. It is not an ordered pair. It is not a point. It is just the x value of x equals. So if I have one does this log equal this absolute value, use Mr. Blinky to solve any crazy equation you see. You can actually use it to solve any equation you ever encounter in this test, but if it's crazy, use Mr. Blinks to find the intersection. It's key if they're asking you to round to the nearest tenth, if they're at nearest hundredth, nearest thousandth. That's a key that Mr. Blinks is going to be a great tool to use. And finally, the last thing I want to mention is even/odd functions. Even functions means you're symmetric about the y-axis. That means I can take the curve and it has perfect symmetry about the y-axis. I can flip it over, I can fold my paper about the y-axis, and it's going to map onto itself. Odd functions are symmetric about the origin. That means I can rotate it 180 degrees about 0, 0. I can take a curve and spin it about the origin, and it's going to land back on itself. So if I can reflect it through the origin or rotate, turn your paper upside down, and you get the same graph by looking at it through the origin, then you know it's an odd function. These are just three kind of random ideas, function ideas that kind of followed us throughout the course. So we can transform any parent function by adding a number on the inside or outside. Inside's opposite, outside's normal. We can find the intersection by using Mr. Blinks. And a function's even if I can fold it on the y-axis and get itself, or it's odd if I can spin it 180 degrees about the origin and it lands on itself. Those are kind of some final ideas that popped into my head related to Algebra 2. Oh, one more random idea. It's 9th grade. Average rate of change. Of course, I'll end my Algebra 2 review by talking about 9th grade. Average rate of change is our change in y over our change in x. It's the slope between 2 points. It's y2 minus y1 over x2 minus x1. Average rate of change is just slope. If you're ever asked to find that for any function, trig, exponential, log, you get your y values and then find the slope. So that's it for Algebra 2. If you know all of this, you should be getting mastery on this exam. Please watch this video, find some practice problems. It's all on you now. Email at me if you guys have any questions. And I would wish you the best of luck, but studying would have been better.